Today we're going to start section 9.5 called alternating series. And this is one of the most common tests that we're going to use when we see AP problems like this. So first of all, an alternating series is a series where the terms go negative, positive, or vice versa. So it's worth noting that if you have negative 1 to the n and you were to start showing what these terms were, if you plug in 1, you get negative 1, plug in 2, you get plus 1, minus 1, plus 1, and this will just carry on. So it is the odd terms that are negative if you just have negative 1 to the n. And then if you make it negative 1 to the n plus 1, because that adds 1 to the exponent, now the odd terms are going to be positive and the even terms are going to be negative. So even terms are negative. And so that's just kind of worth noting. Down the line, we might be trying to find nth terms or find general terms a lot later in this chapter. So this will be something that we can look at. Okay, so what is the alternating series test? It's a test for convergence only. So there will be no such thing as diverges by the alternating series test. It doesn't give the sum. So far we can only find the sum for a telescoping series or telescoping like and a geometric series. And so here's what the alternating series test says. If you look at the absolute values of the terms, so ignore the alternating part, the negative 1 to the n part. If you can look at those terms and show that the terms decrease monotonically, that means the n plus 1th term should be less than the nth term. The third term should be less than the second term. The fourth term should be less than the third term, and so on. The terms have to be approaching 0. So to show that, you're going to show the limit as n approaches infinity of a sub n equals 0. That's just nth term test, right? We survived that. If those three things are true, we're alternating monotonically, and terms are approaching 0, then the alternating series will converge. Right? So determine the convergence or divergence. So let's run through that checklist. First of all, because there's a negative 1 to the n plus 1, these terms are alternating. True. And the next thing I do is the nth term test. Show that the terms are approaching 0. The limit as n approaches infinity of 1 over n. You remember, you ignore the alternating part and just look at the absolute value. The terms are approaching 0. And finally, we have to show that these terms are always decreasing. So it is true that 1 over the n plus 1th term, 1 over n plus 1, is less than the nth term, which is 1 over n. So that's true as well. So we've met the three conditions, and we would just say converges by alternating series test. Now, example B, same thing. This is a negative 1/2 to the n. So remember, this could be negative 1 to the n times 1/2 to the n. Mathematically, you're allowed to do that. If you're multiplying inside of parentheses, the exponent applies to both parts. So this is alternating, and the limit as n approaches infinity of just 1/2 to the n does equal 0, because the fraction will get smaller and smaller and smaller as you raise it to larger exponents. And it's also true that 1/2 to the n plus 1 should always be smaller than 1/2 to the n. So the n plus 1th term should always be smaller than the nth term. So all three of those things are true. So I could say that this series converges by alternating series test. But remember that we've had this series before, probably this exact series. This is also geometric. So I could say, not only do I know that this series converges because it's an alternating series that has all the correct characteristics, but it also converges by the geometric series test because the absolute value of r is between 0 and 1, less than 1, but also I know what it converges to. So I know that this converges to a sub 0, which is 1 over 1 minus negative 1/2, so plus 1/2. 1 over 3 over 2 is 2/3. So geometric series test is better than alternating series test in this case because not only can I say converges, but I can say converges to 2/3 by geometric series test. So they're both tests are valid. If all you're trying to answer is converges or diverges, you could cite either one of those tests. If you're supposed to find the sum, then you have to use geometric series. All right, what about this next one? This is not quite as obvious that it's alternating, but basically anytime you have a negative number raised to an n, that should be alternating. But let's work on this a little bit because if I'm trying to say take the limit as n approaches infinity, it's not 100% clear what's happening here. So let's just know, just to show that you can manipulate these things. We have n and we have, there we go. We have n and we have, instead of -2, we have -1 to the n minus 1 and 2 to the n minus 1. So I've pulled the alternating piece sort of out here. And whether this -1 is in the denominator, whether you divide something by positive or -1, or you multiply by positive or -1, doesn't matter. So I'm just going to put this out in front, kind of. Okay, so the n is up here. Now 2 to the n minus 1, we've done this before with addition. That's 2 to the n times 2 to the -1. But instead of leaving a 2 to the -1 down here, let's put a 2 to the first up here. Okay, so first thing, is this an alternating series? Yes, because we can show -1 to the n minus 1. So -1 to the 0 is 1. -1, I'm sorry, -1 to the first is 1. When I plug in 1, what I'm trying to say is when I plug in 1, I get -1 to the 0 and I get 1. When I plug in 2, I get -1 to the first, I get -1. So this is alternating. Then I do the nth term test. The limit as n approaches infinity of 2n over 2 to the n. Now, I could do one round of L'Hopital's. Let's do that informally. So because this is infinity over infinity, I get 2 over 2 to the n times ln 2. That's definitely 0. I probably could have said 0 to begin with because of function races. But that is 0. And then finally, n plus 1 times 2 over 2 to the n plus 1. Will that always be less than 2 times n over 2 to the n? I think so. 2 to the n plus 1 denominator is going to grow faster than 2 to the n. And 2n plus 2 versus 2n in the numerator, as n gets very large, the plus 2 is, we can kind of ignore that. So yeah, I think that that's safe to say monotonic. So this series converges by the alternating series test. Okay, this example, we have the alternating piece. Then we take the limit to see if the terms are approaching 0. The absolute value of the terms would be n plus 1 over n. So remember, we ignore the alternating piece. Now this limit is not 0. This limit is 1. So it's not that this diverges by the alternating series test. Remember, this limit as n approaches infinity of the sequence. So basically, like, what are the terms approaching? This is just the nth term test. So diverges by nth term test. So if we're looking at an alternating series and it diverges, it's not by the alternating series test. It's always going to be by the nth term test. All right, now we need a calculator for this next part. So if you don't have one, pause, grab a calculator. We can't find an exact sum for an alternating series, but we will be interested in approximating the sum and then also figuring out how far off our approximation is from whatever the actual sum is. All right, so to find the sum of an alternating series, like I said, we're approximating and we're using an nth partial sum, which we've found an nth partial sum before. So approximate the sum of this series by finding the sixth partial sum. Okay, so the sixth partial sum, you're supposed to start by plugging in 1. This means add up the first 6 terms. So if you plug in 1, you get negative 1 squared, so you get 1 over 1 factorial. If you plug in 2, you get minus 1 over 2 factorial. That's going to be plus 1 over 3 factorial, minus 1 over 4 factorial, plus 1 over 5 factorial, minus 1 over 6 factorial. Okay, so this is our sixth partial sum. We're saying that the first 6 terms ought to be reasonably close to whatever the actual sum is here. So let's hop to the calculator and see what this comes out to. You would not be expected to do this, find this value without a calculator. You can find the factorial command in 2 places, although remember, you want to be familiar with the first 5 values for the first 5 factorials. But even so, you can either go to math and over to probability, and then it's down here. Or there are a lot of shortcuts if your calculator's newer and you press alpha and any one of these buttons. So it's alpha window, and there's all kinds of little shortcuts here. Absolute value, derivative, summation we could probably use at some point. But anyway, I'm looking for factorial. All right. Now, 1 minus 1/2 plus 3 factorial 6. So 1/6 minus, I'm going to get a syntax error there. There we go. Plus 1/6 minus 1/24. That's 4 factorial. Plus 1 over 120. That's 5 factorial. Minus 1 over, 6 times 120 I could do, but let's just do 6 factorial. And then we're going to write down what this comes out to. So this is S6 is equal to 0. Write this all out, 6319, and then it's 4 repeating. Normally we round to 3 places for our AP exam, but when we're talking about error and how far off we are, we want to take this out to as many decimal places, unique decimal places as we have, just for comparison. So we know this is not the exact sum. This is an approximation, and we want to know how far off we are. In other words, we want to know what is the error. Are we off by 1, or are we off by 0.5 or 0.01 or 0.00? Like, are the first 2 decimal places accurate or what? So we have a theorem that we're going to use a lot, and we'll use it especially for free response questions. It's called the alternating series remainder. So let me translate this notation that you'll see a lot. The absolute value of S, which is supposed to be the actual exact sum of the series, which we don't know, minus our nth partial sum. So the difference between those two, an absolute value, meaning we don't care if it's a positive or negative difference, just the difference between those 2 values, how far off we are, we call that the remainder. And again, we're putting an absolute value around it because we don't care if it's positive or negative. The value of that remainder will always be less than or equal to, what is a sub n plus 1? Well, if you stop at 6 terms and you add those up for your partial sum, it's the 7th term, the value of that 7th term, like what it calculates out to, that will be your remainder. So a sub n plus 1, we tend to call that the first neglected term, meaning the first term you left off. If you're finding a 6th partial sum, the 7th term is the first one you neglected. If you're finding a 3rd partial sum, it'd be the 4th term that you neglected. Okay, so back to our example. So we want to know the difference between the actual sum and our 6th partial sum is equal to the remainder sub 6, because you used a 6th partial sum, should be less than or equal to the 7th term, n plus 1, 6 plus 1. What is the 7th term? The 7th term is what would have come next. What would have come next is plus 1 over 7 factorial. Now, this is plus, so I'm just going to make a note here. This is the remainder in case you write this in on your notes. So what does that mean? So if if that were minus 1 over 7 factorial, we would still make it positive because remember, we're looking at absolute value. So we could keep absolute value around if we want. Okay, so the difference between our sum, our sixth partial sum, and the actual sum should be 1 over 7 factorial. That's a pretty small decimal. So what is that decimal? That is, let's expand this out as well. So our remainder, when we used a sixth partial sum, how far off are we? 0.000, because this times 10 to the negative fourth, 198,412,6984. What this really means is, look how many zeros there are. Our estimation is accurate to 3 decimal places. And then once you get to that 4th decimal place, that's where our estimation will differ from the actual sum by this much. Okay, so the actual sum plus or minus, our sixth partial sum plus or minus this 0.000198 blah, blah, blah number, that is the actual sum. All right, so we can be told how many terms to use, and then we can figure out how far off we are. Oh, I'm sorry. By the way, the reason that this is true, there's a pretty good video explanation for it that I've linked from someone else on YouTube. We can go into this further in class, but we can check this with a geometric series, like something we actually do know the sum of, and then look at what's happening. Why is it the first neglected term? But the big idea is like, okay, I would have added 1 over 7 factorial, and then I would turn around and subtract 1 over 8 factorial. So I would get a little bit closer. Like I get farther away from the sum, but then I get a little bit closer. And then I would add 1 over 9 factorial, but then I would subtract 1 over 10 factorial. So you kind of zero in on whatever the actual sum is. But the furthest that you'll ever be from it is that plus 1 over 7 factorial. And every term after that, you'll get closer and closer and closer. So the furthest off you could be is whatever this term is. Anyway, there's a better explanation that I've linked, so feel free to investigate that if you are curious. What else do we have to do with error? So another common thing, again, for free response or for multiple choice is to not be told how many terms to use in your partial sum, but instead determine the number of terms required to approximate this series so that you're within 0.001. So they give us the error. This is how accurate we have to be, 2 decimal place accuracy. And we have to figure out, what is that? Is it a 6th partial sum, a 5th partial sum, or what? Okay, so here's what we know. We know that the difference between the actual sum and this nth partial sum, we don't know what n is, that's equal to the remainder for the nth partial sum. That's less than or equal to the first neglected term, the n plus 1th term, and that has to stay less than 0.001. So here's my setup. Anytime I do this type of problem, I write out this line, and the only thing that changes is this error. The next thing to do, remember this nth term, n plus 1th term, is an absolute value. So if we're looking at this sequence, we're ignoring the alternating part, and we're just saying, okay, the sequence, the absolute value, a sub n, absolute value of that is 1 over n times 4 to the n. What would a sub n plus 1 be? Well, plug in n plus 1. You would get 1 over n plus 1 times 4 to the n plus 1. All right. Now I have a calculator for this. If this were no calculator, I would have to change this to 1 over 1,000. And then kind of like guess and check, like plug and chug. That n is not going to be 10 or 11. It's going to be 2 or 3 or something like that. So I would do some math to figure out, like, well, I don't know. When does this denominator exceed 1,000? But if we have a calculator, then we plug this into y1, and then we're looking in the table for which values of n cause this whole fraction to come out smaller than 0.001. So let's type this in first. Go to y equals type it in how I have it here. See how it's 1 divided by, you need parentheses around the whole denominator so that the calculator knows what's down there, that's all in the denominator. So I've got x plus 1 times 4 to the x plus 1. All of that is underneath 1. And then we're going to go to the table. So second graph. Okay, now my table is at something weird. So go to second window. Have the table start at 0. Have it change by 1. Go back to table. Okay, so if n were 0, then our error, our remainder value, would be 0.25. If n were 1, the remainder would be 0.03125. I'm looking for this decimal on the right to be smaller than 0.001. 0.005 is still bigger than 0.001. 0.0009 is smaller than 0.001. 0.00009, what was the rest of it? 765, blah, blah, blah. That's less than 0.001. When did this happen? This was when x equals 3, so when n equals 3. When n equals 3 and you plug this in, you get 1 over 4 times 4 to the 4th. That gives you a fraction or a decimal that's smaller than 0.001. Okay, so determine the number of terms. It's the third partial sum that will approximate this error, or this sum of this series with this amount of error at the greatest. So we're going to say, all right, the sum of the series from 1 to infinity of negative 1 to the n plus 1 over n times 4 to the n can be approximated by the third partial sum. The third partial sum means add up the first 3 terms. So plug in 1, and you're not ignoring the alternating piece. So plug in 1 and you get 1 over 1 times 4. Plug in 2 and you get minus 1 over 2 times 16. And plug in 3, so you get plus 1 over 3 times 64. All right, so we're saying that here's our approximation. So that was 1/4 minus 1 over 2 times 16 plus 1 over, what was the last thing? 3 times 64. Use parentheses down there because I don't feel like doing that math. So we're saying that the actual sum is about 0.2239583 repeating. And we know that that's only off by less than 0.001. So the first 2 decimal places are accurate for whatever this actual sum is. Split this. And again, this is the only time I don't round to 2 places. Oops. This is the only time I don't round to 2 places. So 0.2239583 repeating. That's what we're saying the sum is a pretty close approximation. If we wanted more accuracy, then we would have to add more terms. It makes sense that the more terms you include, the closer to the sum you will be. And remember not to be tricked by trig stuff. So just because a series could have positive and negative terms does not mean it's alternating. Alternating literally has to be one term is positive, one term is negative. The next term is positive, the next term is negative. It can't be a few positives in a row and a few negatives. So sine 1 over 1, sine 2 over 4, you might think, oh yeah, sine goes between 1 and negative 1, but only at its extremes. The sine of 1 is that decimal. The sine of 2, this is 2 radians, right? It's still positive. The sine of 3, still positive. So none of these are alternating. So just be careful of that. In this case, we would need to do LCT or DCT to figure out what's happening here. All right, we're going to stop there for today, and we will pick up on day 2 tomorrow.